Ladies and gentlemen, here is the Chapter 8 presentation. We're going to be talking all about momentum. Momentum is a very simple concept. It's mass times velocity. You take the mass of a moving object, you multiply by the velocity, you get this quantity called momentum. All right? There is your formula for this thing. P, the symbol for momentum, don't ask me why, is equal to mass times velocity. The place where this is useful is in collisions. You can see down here that the cue ball came in. It had mass and velocity. It struck the other pool balls here, and you can see that these things are being moved about, right? From the momentum of the cue ball, the yellow ball is coming this way, and the stripe and the solids and everything moves around. The momentum here is transferred to the other balls, and depending on the mass of these other balls, they will have different velocities. This collision is a really good way to think about momentum, and in particular the idea of conservation of momentum. Not a whole lot that we can do with momentum in and of itself, but this idea of conservation of momentum is hugely important in crashes and explosions and different kind of events like that. All you have to do is say that the total momentum is constant. And if you use that symbol P for momentum, this would indicate the momentum before the collision, and this would be the momentum after the collision. That little tick mark right there says after, right? Momentum before equals momentum afterwards. So looking at the picture over here, I've got a mass 1, it's moving at velocity 1, it's going to slam into the back of mass 2. Mass 2 is also moving to the right. They're both moving to the right, but mass 2 is moving slower than mass 1, therefore it's going to get hit from behind, and that's certainly going to drive mass 2 faster to the right. The speed of mass 2 will speed up. If you were going down the highway and somebody ran into you from behind, you would speed up, all right? Meanwhile, they would slow down. Some of their momentum would be transferred to you, but that would take momentum away from them. So you can see here this mass 1 after the collision has actually bounced backwards, and that can happen and will happen under certain circumstances that we'll take a look at here. But the conservation of momentum is all that we really need to think about here. The total momentum before, I would have mass 1 times velocity 1 plus mass 2 times velocity 2. Take all the momentum in the before picture. It's got to equal all the momentum in the after picture. Mass 1 times v1 prime. There again, that prime means after the collision. The velocity of object 1 after the collision. Over here I'd have to add mass 2 times velocity 2 prime. The velocity of object 2 after the collision. Momentum is always conserved. Any kind of crash, any kind of explosion, as long as you don't have any outside forces, then momentum has to be conserved. And that's a big idea. That's what we want to work with in Chapter 8. Now, this is what we did in the last one. Here's the same picture again, but we said that the momentum before has to equal the momentum afterwards. We said the total momentum in the first picture, so you can see m1v1 would be the momentum of mass 1 plus m2v2 would be the momentum of mass 2. There's my total added up. Total momentum before the crash over here would be the total momentum after the crash, and those have to be equal. That is a nice little equation, and we can work with that. Let's do an example right now. Here, if I have I don't know, we'll let mass 1 be equal to 6 kilograms, and it's moving to the right at 4 meters per second. If I went ahead and calculated its momentum, P1 would be equal to 6 times 4 would be 24. The units here, kilogram meter per second. All right, so that's number 1. Number 2 over here, and we could make up whatever numbers you like. M2 equals 4 kilograms. V2, this, remember, we need a before picture, and then we also need an after picture, but working on the before picture right now. V2, let it be 2 meters per second. Okay, still moving to the right, but it's moving slower than mass 1 is. So it's going to get hit from behind, just like the problem we just did. If you wanted to go ahead and get the momentum here, you don't really have to do this, but I just want to make a point about it. 8 kilogram meter per second. We just leave those units like they are. Okay, for once we don't give it a new name. After the collision, lots of things could happen. Here's mass 1, here's mass 2. Some of the possibilities include the objects stick together and travel as a single unit after the collision. Another possibility would be that they hit and bounce off of each other, and each has its own individual speed. So lots of things can happen here. We believe that mass 2 is going to get sped up, so I'm going to call that V2 prime. And we're pretty sure that V1, the velocity of the first object after the crash, V1 prime, will certainly be slowed down and could even be bounced back in the opposite direction, to the left. So V1 prime is another thing here. Now, all the problems that we do, we will assume that the masses stay the same. So this would be 6 kilograms, and mass 2 would still be 4 kilograms. Nothing changed there. All right. In real life, sometimes things break, or two cars hit and the bumper falls off, changing the mass, something like that. In our problems, the masses always stay the same, and you could certainly handle it with what we're doing. You would just then have 3 masses, and the total momentum would have to be conserved. But let's just do this. I don't know exactly what's going to happen here. We could use some other equations that will come up in just a moment. Let's say that these two objects hit and they bounce. They do not travel together afterwards. And this is going to be a bogus number right here, but I'm going to put it down. Let's just say that we measure V1 prime, and it goes down to 1 meter per second. Okay, now I've done that in red there because, again, I just made that number up. It may not have anything to do with what would really happen in this situation. Okay, but if V1 prime were 1 meter per second, you see how we could find V2 prime? All I have to do here is to use conservation of momentum. So the momentum before equals the momentum afterwards. If I take the total momentum in the before picture, that would be m1 v1. Total momentum afterward, of object 2 would be m2 v2. Then over here I'd have m1 v1 prime would be the momentum of the first object after the collision. m2 v2 prime would be the momentum of the second object after the collision. And I put all that together, I end up with this equation that we've seen on the last slide. And you'll notice that I know all of those numbers except for one. All of them except for v2 prime. So we want to solve for that, and you can see where this is going. The subscripts here are a little bit tedious, but they help keep everything straight. It's a bookkeeping kind of thing. I'm going to subtract this term from both sides. It cancels on the right, comes up over here on the left as negative m1 v1 prime. I could also divide both sides by m2, and that would give me v2 prime over here by itself all alone. Okay, got the numbers. We stick the numbers in. Mass 1 was 6 kilograms. V1 was 4 meters per second. I add to that 4 kilograms times 2 meters per second. I'm just getting these numbers from my picture right there, mass 1 V1, mass 2 V2. Put those in, and I need to subtract mass 1, 6 kilograms, times the speed afterwards. That was that 1 meter per second that we just made up. Maybe that's a good number, maybe not. And then I divide by mass 2, which would be 4 kilograms, like this right here, and that's supposed to be V2 prime. So let's run the numbers, see what happens here. 6 times 4 would be 24. Add to that the 8, it would be 32. Subtract 6, and I'd have 26. I need to divide 26 by 4. All of these would be 26 kilogram meter per second, units of momentum. Divide by the 4 kilograms there. 4 would go into 26 6 times. 6 times 4 is 24. I'd have a remainder of 2. 2 over 4 would be 0.5. My kilograms cancel out, and I've got meters per second there for v2 prime. 6.5 would be the speed of v2 prime if this number is right. Okay, if it really is 1 meter per second for v1 prime. I made that number up. Maybe it is, maybe it isn't. But you can see how if I know most of the numbers here, I can certainly find the other ones. I'm going to have a better way for you to do this that would tell us how fast v1 prime would go and how fast v2 prime would go. But for this first example, I just wanted to demonstrate here that how conservation of momentum works, and that we can use that equation to find some stuff we didn't know before. I want to do one more thing before we move along. Right here, remember how we had 24 and 8 kilogram meter per second of momentum before the collision. If I add those together, that would be 32 kilogram meter per second. I had 32 total kilogram meter per second units of momentum there. I should have 32 afterwards. So let's double check here and make sure that this worked out. 1 times 6 would be 6. And 6.5 times 4, 4 times 6, there would be 24. Half of 4 would be another 2, so that's 26. 26 and 6 would indeed be 32 kilogram meter per second of momentum. And that's what we're trying to do, is to make sure that the total momentum before and the total momentum afterwards is the same number. It has to be, in the absence of outside forces. So here's a special case that you'll want to know about. This is called the inelastic collision, or a hit and stick problem. Inelastic collision is the fancy name for it. Hit and stick is how I kind of remember when to use this thing. Lots of opportunities to use this. Sometimes you'll see train cars, right? So here's a little train car, and it's moving that way, and there's another train car, and maybe it's just sitting on the track, maybe it's going left or right or something. But afterwards, these two hit, the couplings grab hold of each other, and the whole thing, both cars together, move off to the right. This is hit and stick. The two cars hit up here, right? And when they hit, they stick together, and then they move together. They move as one afterwards. All right? So that's a special case. Let's see what happens in that special case right here. We know that momentum has to be conserved. So I have P equals P prime. We've seen that turn into this equation a couple times now. But what you'll notice here is that V1 prime, the speed of this car, and V2 prime, the speed of that car, both afterwards, are the same because they're moving together. So all we want to do here is to define a new variable V prime, and if I replace V1 prime and V2 prime with that new variable V prime, just pick this up and drop it in right here and right there. Since those are the same number, give it another name. That gives me a common factor which I can pull out front, V prime right there, and then I'd have M1 plus M2 that I could distribute that to get back to where I started from. And this is a really nice way to solve problems that are inelastic collisions where they hit and stick. Now maybe you like it written a little bit differently. Probably a better way to write this would be V prime equals M1 V1 plus M2 V2. There's the numerator, and then divided by M1 plus M2. Maybe that's a little clearer than what's typed out there. Either way you want to think about it. You can see that the parentheses down here hold the denominator, hold the numerator together, so it's the same thing. But this is probably a better way to write it. But that's the inelastic collision. Let's do one of those real quick. And right here, let's say we have, a ball of clay. So here's mass 1. And if we let that be 3 kilograms, and it's moving to the right at 6 meters per second, like that. I've got another ball of clay over here. We'll let that one have a mass of 2 kilograms. And its velocity, let's say this one's moving to the left at 2 meters per second. Okay? One's moving to the right, one's moving to the left, and you know right here that those are opposite directions. Therefore, I have to have a coordinate system. I have to have something's got to be negative, right? So I'm going to create a little coordinate system here. Arbitrarily pick one direction to be positive. So I'm going to call to the right positive. Because V1 is moving to the right, object 1 is moving to the right, that would be a positive 6 meters per second. On the other hand, mass 2 is moving in the opposite direction, in the negative direction. So make sure you get a negative sign right there. Okay, that was my before picture. And afterwards, what happens? I've got these 2 balls of clay. They hit, they stick together, and they are going to move off together. Here V1 prime is going to be the same thing as V2 prime, so I'm just going to call that V prime and not worry about the 1 and the 2. This is a perfect example of a hit and stick, which we also called the inelastic collision. And in these special cases, when they hit and stick, we had that special case formula that we just worked up. Looks like that. And I put the numbers in. I've got 3 kilograms. I've got 6 meters per second. I've got 2 kilograms. I've got negative 2 meters per second. Can you see why that negative sign makes a difference right there? If I had a positive number there, I would get a very different number for the numerator. So make sure that you're watching your coordinate system there. Some of the masses on the bottom would be 6 kilograms. I'm sorry, wrong number. 3 kilograms and 2 kilograms, like that. Up top, I've got 18 minus 4 would be 14 kilogram meter per second. On the bottom, I have 5. 5 would go into 14 2 times, a remainder of 4, so that's a 0.8. And this was kilograms down here, so the kilograms cancel. I end up with meters per second, like that. If these 2 balls of clay hit and stick together, then after the collision, they will be moving at 2.8 meters per second, like that. Is that to the right or to the left? It'd have to be to the right. The answer came up positive. That was a positive 2.8, and positive is to the right. So these are very easy to do. Hit and stick, you slap down the hit and stick formula right here, that special case, and you put the numbers in, and you see what happens. Okay? The next possibility I'd like to present here is called the elastic collision. Remember, the other one was inelastic. This is the elastic collision, and hit and bounce is a good way to think about these. When 2 objects hit and bounce off of each other, then each will have its own individual speed, and in a perfect case, we call that an elastic collision. Now, if it's a perfectly elastic collision, if these things bounce off of each other and there's no loss of momentum, there's never any loss of momentum because it's always conserved, and if there's no loss of kinetic energy, sometimes there is loss of kinetic energy, but in a perfectly elastic collision, we don't lose any. That means that we get to conserve both momentum, here's that equation, and kinetic energy would also be conserved. So here's the equation that would look like that. You've got the kinetic energy of the first object before the collision. Add to that this kinetic energy of the second object. Here's the total kinetic energy before the crash. Here's the total kinetic energy after the crash. Okay? I've got 2 equations, and I've got 2 variables that I'm very interested in, the V1 prime and the V2 prime. If I have a crash, what happens afterwards? What would be the speed afterwards? Since I've got 2 equations with the same 2 unknowns, I can solve that simultaneously and find the solutions for it. This is a good exercise to do. It's nonlinear equation here. This is the bottom one is a nonlinear equation, so you need to do a substitution kind of thing, and it takes a little bit of doing. I've got the solutions for you right here, though. This is what the solution to those two equations looks like. If you want to know how fast the first object is going to be moving after the crash, you need to put all these numbers in and do the arithmetic. And if you want to know how fast the second object is going to be moving after the crash, put the numbers into here and see what happens. Okay, so we'll do one of those now. Here, any two things that would hit and bounce will be fine. This will be the elastic collision / hit bounce. And pool balls are a pretty good approximation of this. If I've got mass 1 is 1 kilogram, and it's traveling to the right at 4 meters per second, and then pool ball number 2 has a mass of, let's say that's, I want to make easy numbers here, let's go with 2 kilograms, and we could let that one go to the right at 1 meter per second. Something like that. There's my before picture. Okay. Afterwards, here's ball number 1. It still has a mass of 1 kilogram. What's the velocity doing? Well, we got to do the numbers and see. What is the velocity of ball number 2? These are the questions we want to know. If the masses stay the same, if they hit and they bounce with no loss of kinetic energy, no loss of momentum, that's when we get to use those two equations. So we would come in here and we would say V1 prime equals M1 minus M2 over M1 plus M2 V1 plus 2M2 over M1 plus M2 V2. And that seems a little arduous, but it's just arithmetic, right? It's just adding and subtracting and the like. So we can do this. Putting the numbers in here, I've got 1 kilogram minus 2 kilograms over 1 kilogram plus 2 kilograms. I need to multiply that times V1, which is 4 meters per second. Here's my addition sign. The second term is coming up. Mass 2 was 2 kilograms. I divide by the sum of the masses again. And V2 right here was 1 meter per second. Okay? So this is going to turn into some fractions and stuff, but we can do this. This isn't too bad. 1 minus 2 would be negative 1. I kind of like to go all the way across the top here. 1 minus 2 would be negative 1. Multiply that negative 1 times 4, and I'd have a negative 4. That would be kilogram meter per second. Downstairs, I've got 1 plus 2 kilograms would be 3 kilograms. In the second term, I've got 2 times 1 would be 4 kilogram meter per second. Just go all the way across the top. Again, over 3 kilograms. We always end up with a common denominator here, so nothing too scary. Negative 4 plus 4 is 0 kilogram meter per second. And the kilograms cancel. 0 divided by 3 would be 0 meters per second. Now, I didn't really intend for that to happen, but it's a beautiful thing when it does. The first ball hit the second ball and stop dead in its tracks. That can happen. That can happen. If I did my arithmetic right here, you may want to check over it again. But I think it's okay. Let's see what ball number 2 did. Here, V2 prime is equal to 2m1 over the sum of the masses times V1 minus the difference of the masses over the sum of the masses times V2. And I'm going to have to get tricky to get all this in here, but 2 times 1 over 3, all of that times 4, minus 1 minus 2 over 3 times 1. And here I would have a 2 times 1 is 2 times 4 is 8. So here's 8/3. Watch your signs really carefully here. 1 minus 2 would be -1 times 1 is still -1. I'm subtracting a -1, so that's like adding 1/3 here. This would be 9/3. 9/3 is equal to 3. Okay? And that would be the speed that I would get right here, 3 meters per second. Okay? Now that problem that we did at the beginning there where I made up a number, right, and said this may not be the right number, you see how you can really come through and do it this way and get the right numbers? We just made that number up several slides back just to kind of show how this works. But if it's a hit and bounce, if two things hit and bounce, then this is a really good way to do this. Let's double check our conservation of momentum here. Mass times velocity here, 1 times 4 would be 4 units of momentum, and I'm adding 2 times 1 would be 2. I've got a total momentum of 6 before the collision. Down here, multiplying 1 kilogram times 0, so that would be 0 units. Here's 2 kilograms times 3 would be 6, and 0 plus 6 would be 6. I've got the same amount of momentum before and after the crash, so that worked out nicely. All right. All of the collisions that we have done have been in one dimension. They're in straight lines, but you could also have two-dimensional collisions or even three-dimensional collisions, right? We can do those. They're not too bad. The only thing that you have to remember here is that momentum must be conserved in the x direction and in the y direction. So where I have these two balls, the red ball comes down at an angle like that. You can see that that downward motion of the red ball means that I have momentum in the y direction. And I've got to have conservation of momentum up and down. I've also got to have conservation of momentum left and right. So what I need to do here is to come in and make sure that P equals P prime. Okay, that's just conservation of momentum, but I need to make sure that P sub x equals P sub x prime and build an equation for that. And I need to make sure that P sub y equals P sub y prime. Now there's two possibilities here. Possibility A is that those two objects hit and stick. If that's the case, I've got a special case formula, right? Possibility A, they hit and stick, and I use the hit and stick special case. Use the inelastic. Possibility B, the two things hit and bounce like pool balls would. And in that case, then I need to use the elastic collision, that last thing that we saw on the last screen. Okay, so let's try one of these, some two-dimensional collisions here. Anything can happen. I would like to, let's do a car this time. Here comes a car this way. I'm looking straight down on the car. And it has a mass of 1,000 kilograms. It has a velocity of 10 meters per second. And we'll say that velocity is to the east. If I had a second car, I'll make a truck this time, how about? So here comes a truck, and it's moving to the north. Here comes some numbers for you. Mass 2 might be 1,500 kilograms. Velocity 2 is 8 meters per second north. These two vehicles come and they crash. And then the question is, what happens to them? Do they hit and stick or hit and bounce? Let's do a hit and stick here. This will be a two-dimensional hit and stick. That's honestly the easier case, because when they hit and stick, we have the hit and stick formula, which is only one thing instead of two things, right? I don't have two individual velocities. I just have a single velocity. But what we're interested in is the pile of junk that is going to go off this way. We know it's going to go off that way because this car has momentum in the x direction, so the pile of junk has to have momentum in the x direction. Meanwhile, the truck has momentum in the y direction, so the pile of junk has to have momentum in the y direction. And it's going to push it to the right and up. We'd like to know the velocities of that. So what we do is we come in here and we say, well, I know that momentum has to be conserved, like that, but I want to make sure that that happens in the x direction, and then I'm going to have to do it again in the y direction. Okay? So I'm going to end up doing this twice. This is a hit and stick, so I get to use the hit and stick formula. Some little subscripts here would keep me straight. Px equals p sub x prime, and then later on down here I'll have py equals py prime, and I only want to use the x or the y components of the velocities. So eventually we'll need to think about those and write out what that would mean. But it is a hit and stick, so I'm going to go ahead and write down the hit stick formula. V prime equals m1 v1 plus m2 v2 over m1 plus m2. When two things hit and stick, we get to use that equation. The only thing is I've got to do it twice. And the difference between the two, again, is that up here I only want the x components of the velocities, and down here I only want the y components of the velocities. But other than that, it's exactly the same. Let's break out v1x and v1y down here. With this one, I picked something kind of easy here because one, the red car is all in the x direction. It's headed east, right? That's straight along the positive x-axis. So when we see v1 is equal to 10 east, we can say that's 10 meters per second. How fast is the car headed north or south? It's not. So right here, the y velocity would be 0. Similarly, over here for the truck, v1x, v1y, I need those two pieces. The car is headed north. That's in the y direction. So that 8 meters per second would be here, and 0 meters per second would be right there. It's not headed east at all. It's not headed left or right at all. Okay? You have to separate out x and y, just like everything else we've done this semester. If it's happening in 2 dimensions, separate it out and treat each independently. Now we're ready to put these numbers in. Mass 1 was 1,000. Velocity 1 in the x direction is 10. Mass 2 is 1,500. The velocity in the x direction right here is 0. Okay? 1,500 times 0 is 0, so that one cancels out. Downstairs, I need the sum of the masses. Here, that would be 2,500 kilograms. And I have, 10,000 divided by 2,500, which would be 4. And I'm going to double check that there, but that's got to be the right answer. Yeah, big dummy. I knew that. 4 meters per second. Left some units out there and whatever. We're looking for a velocity. It's going to have to be that. Okay? When I do the same thing down here, I only want the y components of my velocity. Mass 1 is 1,000 kilograms. V1y, I'm looking for V1y. Where is it? It's not 10, right? V1y is 0. So get the right number in there. That's the point of doing the picture and writing all that out. Plus, mass 2 is 1,500 kilograms multiplied by V2y. Go look for V2y. It's over here in our picture. It's the 8 meters per second. Divide by the sum of the masses again. And here 1,000 times 0 would be 0. 1,500 times 8 would be 8,000, and I guess 4,000, 9,000 divided by 2,500 would be 1500 times 8 divided by 2500 is I guess it is 4 point something. Yeah, 4.8 meters per second. 1500 times 8 divided by 2500. Looks good. Okay, so I'm not done with this, believe it or not, but we have the x velocity and we have the y velocity, and we've seen this kind of problem before. We know exactly what to do with this. We're going to come in here and think of this as a new triangle. It's moving 4 meters per second this way, and it's moving 4.8 meters per second this way. And you see how we want v prime. We want that hypotenuse. We want we need to do the Pythagorean theorem on this thing. So v prime is going to be equal to the square root of 4 squared plus 4.8 squared. I got a calculator here somewhere. Where is it? Square root 4 squared plus 4.8 squared is 6.24. meters per second. I'd like to know the angle so that I can talk about this as being a vector. To be a vector, I'd have to have both pieces. So I've got the opposite. I've got the adjacent. That pushes me in the direction of tangent. And here I'm looking for the angle, so arctangent. I need to take the arctangent of the opposite, 4.8, divided by the adjacent, 4. And we will do that right now. Second tan, 4.8 divided by 4 is 50 degrees. So now I've got my magnitude, I've got my direction. I can put those together as a complete vector, knowing the magnitude and the direction there. And that's what you'd have to do for a two-dimensional crash. Okay, a little more work, but with 2 dimensions, I separate out what happens in the x direction and the y direction. I do whatever happens here. Because it's a hit and stick, I get to use the hit stick formula, and I get a solution. Here's the solution in the y, and then I've got to go back and put those 2 pieces together, and we know all about doing that. So there's one of those. I'm going to set up at least one more of these. This one was kind of nice because they were already pointed east and north, and so it was kind of easy to set up the to find the initial velocity in the x and the y direction. If they're not headed in a cardinal direction, then I have to do a little bit more with this. Sorry, let me go back and do this. Right here, let's say that I had a pool ball that's headed down like that, and maybe the velocity of pool ball number 1 is 6 meters per second at an angle of 320 degrees, measured relative to 0 here, counterclockwise around. Pool ball number 2 might be 2 meters per second at an angle of 30 degrees. I still have to get the x and the y components of this. Now this is a pool ball. These are pool balls. So this is more likely a 2-dimensional hit and bounce problem. Okay? Which means I have to do the hit and bounce formulas instead of the hit and stick formulas, the elastic case instead of the inelastic case. And you remember that that had 2 parts to it. V1 prime equals all that mess, M1 minus M2 over M1 plus M2, V1 plus 2M2 over M1 plus M2, V2, all that, right? Okay, and then I had to come back with V2 prime and 2M1, all of that stuff right there, right? Why don't we just find the velocity of ball 1 after the crash here? okay? Which means that when I do this in 2 dimensions, I've got to do it twice. I got to do the whole thing twice. So when I've got all these parts, I'm really going to have v1x prime and v2x prime, right? I'm going to have to do all that. And then I also want to do v1y prime and v2y prime. And I'll have these same formulas here. And when I do ball number 1, V1, this is my equation. And then ball 2 would be that 2m1, blah, 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 like this, right? In the top one, I have up here, I want to do for the x direction. So that means I need some little subscripts. I've already got the x right here and right here, but these velocities need to be the x components, right? These ones would have to be the y components. And then right here, I'm sorry, that should be x. Sorry. Okay. Down here on the bottom, I'm doing the y direction. So both of these subscripts are y right here. That means that the velocities here, I only want the y components here, right? And then what I'll have to do is to take this piece and put those together, right? What we'll find is how fast this ball is moving to the right and how fast it's moving down, like that. And I'll have to combine those. And then I'd also have to find out how fast this ball is moving to the right and how fast it's moving up. And I'd have to put those together. But let's not worry about ball 2. Let's just do ball 1 here, and you can see how that would work. That means that I can make myself some room here, and that's why I didn't write all this mess out, because I'm just going to erase it anyway. Okay? But let's find the speed of ball 1 in the x direction after the crash, the speed of ball number 1 in the y direction after the crash, and then we'll put those together. And you would have to do the exact same thing for ball number 2 right here. Here we go. I haven't given you any masses, so let me do that. Mass 1 is 1 kilogram, and mass 2 is 2 kilograms. Okay? Now, sadly, we got one more thing we have to do before we can really get busy with this. See how I need V1x and V2x, V1y, V2y? I don't have those numbers yet. Okay? What I've got is a polar notation here for the velocity of 1 and a polar notation for the velocity of 2. So I've got to separate those out before I can do anything else. We see that V1x would be the adjacent to that. So here V1x would be 6 times the cosine of 320, and V1y would be the opposite over there, 6 sine 320. And then down here I'm going to get all these numbers and we'll go get the values and see what happens. V2x would be this side right here. That's adjacent to that 30-degree angle. So here I'd have to do 2 cosine 30, and for the y component I'd have 2 times the sine of 30. And again, I've got to have those numbers. I've got to break it out into x and y so that I've got all of these parts and pieces to put into my thing. 6 cosine 320 is 4.6. 6 sine 320 would be negative 3.9. Notice that is headed down, so a negative number makes good sense there. 2 cosine 30 is 1.73. We'll just call it 1.7 meters per second. That's to the right. It should be positive. And the last one, 2 sine 30, would be 1. It's headed up, We got a positive number, looks pretty good. Now we finally have all our numbers. Now we can finally start shoving stuff into the equations, and nobody said it was pretty, but it's worth it. So here we go. 1 minus 2 over 1 plus 2, V1x is 4.6, plus 2 times mass 2 is 2 kilograms. Down here I've got a 1 plus 2, and in the x direction, ball number 2 is headed 1.7. Okay? When I do V1x, make sure you get V1x. When you want V2x, get V2x, and you put those numbers in. Alright, so I'm going to do that up right now. The top one here would be let me put some parentheses here. Actually, this would be negative 1 times 4.6 divided by 3. And then I want to add to that 2 times 2 times 1.7. And that's all divided by 3. I get a 0.73 meters per second in the x direction. When I put the numbers in for the y direction here, I would have 1 minus 2 over 1 plus 2. V1y, where's that number? V1y is negative 3.9. Plus 2 times the second mass, that's 2 kilograms, over 1 plus 2, times V2y, which was 1. So here we go. This would be negative 1 times a negative 3.9. Negative times negative would be a positive 3.9 over 3, plus, and here I've got a 2 times a 2 times a 1 would be 4, all over 3. So that's a 7.9 over 3, and that's 2.7 or something like that. Let's see what it is. 7.9 divided by 3, 2.6 meters per second. Okay? I wanted those two parts. And remember, we're only doing ball 1, so you'd have to do all this all over again for ball 2. But for ball 1, we see that we're moving 0.73 to the right, 2.6 up. So what I want is the hypotenuse of that. And I would do the Pythagorean theorem. And if I can remember my numbers, we'll do that. Square root of 0.73 squared plus 2.6 squared is 2.7. So this would be V1 prime. The velocity of ball 1 after the collision is 2.7 meters per second at an angle. We're going to do arctangent here again. Opposite 2.6 divided by adjacent 0.73 would be 74 degrees. Okay? When these two balls come down here and hit, right, this ball's coming this way right here, the other one's coming this way, ball number 1 is going to bounce and go up something like that. Ball number 2 is probably going to bounce and go down the other way somewhere. Okay? And you could go through and find that number, the magnitude, the velocity of all that. You can see the importance of these kind of things. These collisions are important. If two cars hit and bounce, you could find out how fast the cars were moving beforehand. The cops have the little wheels in the trunk, right? And they'll roll them along the ground, measure the skid marks, and from that they can work out, well, the cops can't, but they have a computer program that somebody wrote that will tell you how fast the cars were moving beforehand. And you can look up the if it's a Lincoln Town car from 1973, you can, the database has that mass in it, and you measure the tire marks, and whether it was raining or not would determine how much friction you have, and you can work out the velocities after the collision and work back to get the velocities before the collision. So, that way the right person gets the ticket. So good stuff. All right. Next thing I want to tell you about here is impulse. Impulse is a very simple idea. It's force times time. All right. That's the equation that we want right there. Impulse equals force times time. So think about what that would mean. If I apply a force to an object, it accelerates. And if I applied that force for a longer period of time, then it would accelerate for a longer period of time, and it would gain more velocity, and it would cover more distance and all of that, right? Can't really do a whole lot with that number by itself. But what is a handy thing is this right here, which is sometimes called the impulse momentum theorem. Momentum, there we go, theorem. Okay, the impulse momentum theorem is really nice because sometimes we know how much force is applied to an object for how much time, and now we can say if it had a certain mass, the final velocity here, the initial velocity is there. This is the change in momentum. So for example, if I had a car that were traveling at one speed, v0, and I want it to speed up, right? V over here, as those go up, I'm going to have to apply a force to the car. I can either get out behind and push it, or I can step on the gas pedal and let the motor push it for me. But there's got to be a force, and the time that I apply that force determines how much my velocity changes. For V0, it's going to go up to V, and the force is what does that. The longer I apply the force, then the higher the V gets. So this is a really nice formula to use. We can do this here in a example if you like. We'll do the car again, I guess. Here I've got a car that's traveling at 20 meters per second, and I'm going to apply a force of a net force here of 600 newtons. Let's do that for 4 seconds and work out what the final velocity of the car would be if the mass of the car is, say, 1,000 kilograms, something like that. Okay? If you see something changing velocity in Chapter 8, it's a good time to start thinking about impulse momentum theorem. Also, this is the only place in Chapter 8 that we have force and time. So that might be even a bigger tip-off. If you see force and time in a problem, then you need to think impulse momentum. Okay? Force and time. Right here we got force and time. So I'm going to write down the impulse momentum theorem like that. Specifically, we're trying to solve this thing for the final velocity, so I'm going to add that to both sides. That would leave me a mass times velocity here, and then I could divide by the mass, so force times time plus mass, velocity naught divided by mass equals the final velocity. Here are those numbers: 600 newtons, 4 seconds. I've got 1,000 kilograms of mass that initially was moving 20 meters per second, and I divide by the 1,000 kilograms here. And where's my, how do I do this? 604. So parenthesis 600. There's my force times time plus the mass times the initial velocity. Close up the numerator, and we're dividing by the mass. Now I'm up to 22.4 meters per second. Okay? That would be my final velocity there. If I apply a force of 600 newtons for 4 seconds, I pick up a little bit of speed. If I applied it for 8 seconds, I'd pick up a little bit more speed, right? Or if I applied a larger force for 4 seconds, I'd pick up more speed. But the engine of the car has to do that work. And force and time, if you see force and time, try impulse momentum theorem. Here's a topic that's not actually in your book, but I wanted you to see it. I think this is an important idea. We've talked about perfectly elastic collisions where the objects get to keep all of their kinetic energy. Kinetic energy is completely conserved. So we have this number called E, which we call the coefficient of restitution. In perfectly elastic collisions, we say that E is equal to 1, meaning that the conserved or the kept kinetic energy is 100%. All right, I get to keep all of the kinetic energy in that case. Kinetic energy is conserved. Down here, if it's perfectly inelastic, I can lose all of my kinetic energy. Let's say that you had a ball of clay and a ball of clay, and they were going like this, and they hit and they stuck together, and they just stopped dead in their tracks. Right? That could happen. I have no kinetic energy afterwards. So this is how much kinetic energy did I keep? Kept kinetic energy equals 0%. The coefficient of restitution is 0 right there. Well, real life happens somewhere in between those two ideal cases, right? In the picture here of the dropped ball, if I drop a ball from this height and it comes down, if it were perfectly elastic, I would keep all the kinetic energy, so it would bounce back up to the original height, and then it would do that again, and it would just bounce forever to the same height, right? But in real life, we see it do something like this, and it will get a little bit lower and a little bit lower each time. It loses some kinetic energy, and it doesn't go back up as high as it started. Okay. If it were perfectly inelastic, what would happen? The ball would fall, and it would stick to the floor, and you wouldn't get any bounce. So here, this thing is somewhere in between those two ideal cases. And you can think here of kind of a continuum, a spectrum, where I get to keep all of the kinetic energy, or I lose all the kinetic energy. A red rubber ball from the machine in the grocery store might be right there. I might get to keep 80% of my kinetic energy. A tennis ball might be 60 or 70%. If I drop a biscuit on the floor, maybe I get to keep 10% of it, So this coefficient of restitution can go anywhere from 0 to 1. All right? But I can't have more than 100%. I never get to keep more, and I can't have a negative number here. So there's two ways of thinking about this. This last one is for a dropped object. If I drop an object from some height h and it bounces to some height h prime, then I can take the square root of that ratio, and that will give me the coefficient of restitution. On the other hand, if I have two objects that crash together, here's a ball coming this way at V1, and here's a ball headed some direction at V2, right? There's my before. Afterwards, I would have V1 prime and V2 prime. If I take the ratio of the velocity, the difference of the velocities after the crash divided by the difference of the velocities before the crash, then that's another way to get this coefficient of restitution. So this one that I've circled up here would be two objects colliding, and the other one would be for a dropped object. Okay, two different ways to think about it. Again, that's not in the book, but it is kind of an interesting idea. We have these ideal perfect world cases, it perfectly bounces or it perfectly sticks. Real life is always in the middle somewhere. So I just wanted you to see that. Okay, so that's pretty much it for the 201 people. If you're in 221, I wanted to tell you a little bit about center of mass, and the 201 people are welcome to listen in. The center of mass is a important idea. When we talk about these problems, we act, momentum works as if the object is a single point mass concentrated at the center of mass. What they've done here is they've drawn a little dot on a hammer. Right there is the center of mass. If you held that hammer up, you could put your finger underneath that point and the hammer would balance on your finger right there. That's kind of what the center of mass is. Where would that object balance? If I keep that dot, right, for all of these cases, can you see that when I throw the hammer, it can spin, it can rotate, it can do whatever it wants, but that center of mass follows the nice parabolic trajectory that we expect from our equations. Okay? So we're really saying whatever funny shape the object is, just think about the center of mass of it. There are several ways to find center of mass. Here are some shapes. Back when I used to do some lathe work, if you wanted to find the center of a stock, a piece of wood or metal or something, you could come in here and with a square especially, or a rectangle, you can draw a line from diagonal to diagonal, and the center of mass is going to be right there, right? And you could do the same thing with a circle, with a triangle. You could take your finger and, with some kind of plate, triangular plate, you could hold your finger directly underneath a point, and it would balance right there, and that would be my center of mass. That's a crummy picture if ever there was one. Here's a second way to get the center of mass. If you hang up the object, let's say we suspend this object from this point right here, and the string comes down across there. If I mark that line, and then I turn and I hang it from a different point and mark that line, and here's the old line, right there's my center of mass. So I can do this thing experimentally and find where that is, or I could balance it on my finger or something. I've got the picture of the donut there because that's kind of an interesting shape. If I find the center of mass of the donut, the center of mass is actually not part of the object, so sometimes that happens too. One more slide and we'll be done here. If I have a weird shaped object, and I'm looking at this thing over here, maybe this is a piece of metal, right? We've taken plate steel and we've cut this shape out of it right here, and I need to find the center of mass of this thing, but I can't cut it up into pieces, and I want to do it mathematically. I don't want to just balance it on my finger or something. Maybe it's too heavy for my finger, right? What we want to do, there's a couple steps here. The first thing that we need to do is to cut this object up into pieces, and you can see that if I cut this line and this line right here, we're just doing this mathematically. We draw the object and mathematically cut it up into pieces. Then I need to pick a coordinate system origin. That's step number 2. Maybe I want to pick this point right here and say that's 0, 0, and I want to measure all of my, here goes the x direction this way and the y direction that way. Find the center of mass of each one of those pieces. So the red dot right here would be the center of that piece, and the blue dot and the green dot are the center of masses of those pieces. And then step 4, we can come in here and we can find the x center of mass, the x coordinate of the center of mass, and find the y coordinate of the center of mass. And if needed, you could find z as well. On a flat thing, you'd probably just do the first 2 of those. Let's do one of these real quick. Here is a piece of plate steel that we have like this, and let's say that the whole thing weighs 300 pounds. All right, and I'm going to make up some numbers here. Maybe this thing is 8 feet this way, and it's 8 feet this way, and then I've got a 4-foot piece here, and this is a 4-foot piece. This would be 4 and 4 right there. Okay, I'd like to find the center of mass of this thing. So like we said, first thing we're going to do is, at least on paper, cut this into pieces. If I cut that little piece off, now I've got 2 rectangles, and I could find the center of mass of the first piece, and I could find the center of mass of the second piece. I need to have a coordinate origin here, so let's pick that. You could pick any point you like, but then you're measuring from that point, right? So if I go halfway over, we're assuming that this is uniform density, and plate steel pretty much would be, so that's a safe assumption. Halfway over to 4 would be 2 feet to the right. Halfway up 8 would be 4 feet. So 2 feet, 4 feet would be the distance. I need to go 2 feet over and 4 feet up to get to the center of mass of that thing. I need to find the center of mass of the other piece, but remember, I'm measuring from the origin, so I'd have to go 4 feet here and then another 2 feet. So that's actually 6 feet over, and halfway up 4 would be 2 feet there. So the center of mass of that would be found at 6.2 relative to this point right here. And now I can come in here and find the x center of mass, the x coordinate of the center of mass. This was the notation that they do. Sum up all of the pieces from 1 to n, m sub I, x sub I, over the total mass of the object. Okay? All we're really doing is saying take the mass of this object times its x right there, and the mass of this one. I've got 2 pieces, right? So in my case, what we're going to do is we're going to say mass number 1 times the x coordinate of piece number 1, and then mass number 2 times the x coordinate of piece number 2, divide by the total mass. This right here, if I cut this, and again, uniform density, this would have 200 pounds, and this would have 100 pounds right here, right? The whole thing was 300 pounds, and we could divide that out by the area if we didn't have something that was so nice to work with here. But mass 1, the big rectangle, is 200 pounds. X1 is 2 feet over from the origin. Mass number 2 is 100 pounds, and it's 6 feet over from the origin. And the total mass is 300 pounds here. So that would be 200 times 2 is 400, plus 600 would be 1,000 foot-pounds, divided by 300 pounds. Pounds cancel, and that would be 3.33 feet. Okay, so my x, to get to the center of mass, I need to start here and go 3.3 feet over. That would be somewhere like right there. Now I still got to do the y part too. So y center mass would be equal to mass 1 y1 plus mass 2 y2 over the total mass. And so that's 200 times 4 plus 100 times 2. And here again, remember, I'm picking the y values, 200 times 4, 100 times 2, and I want to divide by the total mass, which was 300, and that would be 800 plus 200 is 1,000 over 300. Again, 3.33 feet. So I need to go over 3.33 feet, and I need to go up 3.33 feet. Center of mass would be right there. At those coordinates, and whatever shape you had, if you needed to make 15 pieces, you could do that or something, but that would be how you'd find the center of mass. Very good. Thank you very much. Have a good day.